Do you have experience on that?
Um,
Spider biting?
aren't too many dangerous ones around here, so yeah, not really.
Yeah, I think I got bitten by something. I mean, it's got swollen on my ankle, but
Is it like a bunch of little bites next to each other?
yeah, just two. And it got swollen, and I don't know. If you were itching right now, but
Could be that. I know that whenever
Yeah.
you get bit by them, it's usually a bunch of bites all in one spot.
That's how spiders bite, like they do a bunch of bites.
Yeah, usually.
I was thinking that I can become Spider-Man, just like you, like become Superman, but nothing happened yet.
I feel far from Superman.
I'm thinking I can come to the building in a faster way, but nothing.
No, that
I still need the scooter.
I think just coming to the building without sweating is a superpower.
If you have the scooter, you don't have scooter. Shall we start or wait for another 2 minutes? Yeah, let's wait for another 2 minutes. I have no idea online. I mean, there's some student online. I mean, not talking with you guys. Okay, I'm talking with the online students. So first off, I apologize that the camera doesn't work properly last time. So this time they fixed the issue, and right now you can see the whiteboard. Let me know if you still have some issue when seeing or hearing my lecture. Okay. So regarding the last introduction lecture, I mean, actually we not cover too much important information last time, but I just give you your outline of the class. But anyway, so I will upload the slides, few slides. I mean, on the Canvas. So for the online students, hopefully I can finish the job this week. Okay. But anyway, so it's just like the global view of the class we're going to talk about. So you will not miss anything important through the last class. We're going to talk about in details through the entire semester. Okay. You know that last semester I only had one student involved in the class, and then that's neither join the online section. Then I need to talk to the air through the entire semester. It's really good. All right, so shall we start, everybody? Okay, so we're going to talk about the first law of the thermodynamics. Okay. So as I mentioned previously, the first law of thermodynamics actually just the conservation of energy. We mentioned, right? And the other thing is that briefly, okay. We just for this class we just confine ourselves to the gas. Okay. In that case, so we only have two catalog. We only consider two catalog of energy. Okay. So for the we talk about the internal energy. Okay. So we are not talking about mechanics. Okay. We are talking about thermodynamics. So we do not talk about potential energy, gravitational potential energy, electrodynamic forces. We don't talk about them. Okay. We are dealing with a gas, a liquid, or solid. Okay. So what do we care is the internal energy. Okay. Internal energy. Okay. So basically, that is the energy got held by a piece of research object. Okay, it can be a tank of gas, a cup of liquid, or a solid piece in my hand. Okay, it doesn't matter what it is. So we talk about the more abstract. Okay, internal energy, basically an object or a research object. Okay, I mean the research object can be gas. Okay, it can be gas. It can be liquid. Okay, it can be solid. Okay, we do not talk something else. Okay, we don't talk something. We don't talk about plasma. Okay, that's beyond the scope of our class. Okay, we talk about the internal energy of gas, liquid, solid. Okay? Basically, we can catalog the internal energy. Not catalog. Okay, so we're talking about how can we change the internal energy. Okay, how can we change the internal energy? Basically, confined to our class, we have two methods to change the energy. What's the two methods? I already mentioned last time. Work and what? And heat, right? Heat transfer, right? So basically, we have two ways to do the job. Okay? To make the du, then we have two methods. Okay? We can, let me draw it. So if we have an object, for example, we have a gas, okay? A gas tank. And on top of the gas tank, we have a piston, right? We can either press, change the position of the piston, right? So basically, this is what? This is the work, right? Okay, we label it that what? As delta, I mean in the textbook, okay? It's labeled, I mean last time I used the D with a bar on it, but in the textbook they use this as delta. So it doesn't matter, I just use this label on textbook. Just I don't want to bring actual trouble to it. Okay? So this is delta. Okay. So basically, a small variation of the work, okay? And the other way to change the internal energy is what? Is heat, right? So we can probably put some flame here to warm it up, okay? Sorry for the back drawing, but anyway. So this is heat, okay? This can be labeled as delta. Probably, yeah, we can put a lowercase q, doesn't matter. In the textbook, it's a lowercase q, doesn't matter. Okay? So remember last time we were talking about the, what is the thermodynamic parameters and what is non-thermodynamic parameter, okay? Both work and the heat, they are, neither of them are thermodynamic parameters, okay? So it's not depends on the, we cannot use them to label or describe the state of an object. Instead, it's the process parameter, okay? It depends on the process, depends on the history of the system experience, okay? So give me an example. So remember that for the ideal gas, so if we can put the as the this is the V and the y-axis we can label as P, right? So the work done by the ideal gas is what? Is the equals to P dV. Okay? I will tell you why we get this equation, but right now, let's accept that the work we do to ideal gas or ideal gas performed to the other object is expressed as P dV. Okay? Then we have several paths. For example, the final state is here. This is the initial state is P1, V1, and the final state is P2, V2. Then the work done by the gas is just, for example, is through this path. Okay, this path. Okay. Then the work done by the gas is just an area underneath this curve. Correct? You got this integration, right? Correct? But we have different paths, right? You can select different paths, and you can see the area different, right? That means the total work done by the gas or done by the object depends on the pathway, correct? So it's not, that's the reason the work is not a thermodynamic parameter, okay? It's a process, okay? It's a process parameter. The same argument to Q, okay? But first of all, but I don't want to draw the picture of Q, okay? Because if you want to draw the picture of Q, we need something else, okay? P and V doesn't, we cannot, I mean, represent the Q in this kind of chart with V and P, okay? In order to draw the picture of the Q, we need to know the entropy and temperature, okay? That's beyond what we're talking right now, okay? But eventually we're going to talk about it, okay? We know that actually is what the Q is what? Is the TDS, right? Right? And then this one becomes S, this one becomes P. Then we can draw the Q in the figure, okay? But right now, we are not talking about this. But the other thing very important, you should know that although the work cannot be defined or cannot be identified as a thermodynamic parameter, but it can be expressed as a function of other thermodynamic parameters. Okay, P is a thermodynamic parameter and V is a thermodynamic parameter. Okay, so but this one is not. Okay, it can be expressed as a function of the thermodynamic parameter. Okay. Anyway, so what's the first law of thermodynamics tells us? It tells us the change of the total internal energy equals to what? Equals to how much heat we give to the system, correct? And also how much work we perform to the system, okay? You know what I'm saying? This is the work we've done to the system. The system is the object received work, okay? However, most of the case, this is a little bit confusing, you know what I'm saying? It's a little bit confusing. So instead of define this one as an object received work, we prefer to define as this is a subject who do the work. You know what I'm saying? So basically, this one do the work to the external environment. In that case, we always flip the sign. You know what I'm saying? And then you should be very careful. This work means the work done by the system to the external. If you use the plus sign, then it's the work done by the external to the object. Both ways are working. Both ways works fine. But you only choose one definition for your study, for your future work, okay? But inconsistent with the textbook, we use a negative sign. That means this is the work done by the system to the external, by the gas or liquid or solid to the external environment. Okay? This one gives the work. This one performs the work. Is that clear? Yeah.
So it doesn't matter which one we choose as long as we stick to one?
Yeah, it just stick to one.
Because if it's work being done by the system, then it's expanding, and wouldn't that then be positive? But if it's work being done on the system, it's collapsing, so would it not be negative? Don't we have to change the sign's respective to what's going on?
Yeah. If you change the object you study, you can change the sign, but you always select one design. You always only select one definition. You know what I'm saying? First of all, you need to define the object you want to study, and you want to define which one is external environment. We have a tank here, right? All the other stuff outside the tank we can define as an environment or external factors in external objects, okay? And then all the work done by the cylinder, by this gas, by the liquid. If we put a negative sign, that means the work done by this liquid to everything else outside. Okay? For example, we have a piston, then we also have the gas outside, right? If we press, for example, if we press the piston here, so then what? The volume becomes smaller.
But then the pressure goes up.
Right? The pressure goes up, right? So what's the direction of the pressure? The direction of the pressure is this direction, right? And the displacement is this direction, correct? Right? So in that case, this one, you can see the P dV is positive or negative. It's negative, right? It's negative, correct?
Right.
Because the dV is negative, correct? The dV is negative. Then we have another negative sign here, right? That means if the volume of the gas got shrink, becomes smaller, then the external doing some work to it, and the internal energy increase. Correct?
Okay, so we just change the sign depending if like the piston's going down or if it's going up.
No. You do not change this sign. You do not change this sign. And whether it's going up
Why
or going
change the sign of
down
the work
is determine the sign of the V.
I see what you're saying.
Yeah. But anyway, so right now let me go. Actually, that's the question I'm going to talk about. Anyway, so specific to the ideal gas, okay? For the ideal gas, the delta W equals to P times dV. Okay, P times dV. Okay, so what's the reason? Do you understand why it looks like this? Why is the work equals to P times dV? Everybody knows or not? From mechanical point of view, equals what? Equals to F times dl, right? This force is displacement, of course, you can put the vector sign there, right? And what's the F for this kind of simple case? Area, okay? This is the piston area, okay? But we give it, it doesn't matter. We don't worry too much about the vector sign, but you know that you can also define the vector of the unit, of the area, doesn't matter, okay? And then this one, then the equals to what? P times A times dl, right? And this is A, this is the area of the piston, and then the L is the displacement, right? This is the change of the volume, okay? These two parts become the change of the volume, correct? All right, so we put this one back to the equation. Then we have du equals to delta Q minus P dV. Okay? Right now, let me repeat re-answer your question. Look at the system, okay? Let me remove this part. Draw this one. So we have a tank. We have tank, okay? We have a piston here. So if I press this piston down, if I press the piston down, the dV is negative or positive? Negative, right? The dV is negative. Okay, if I press it down, correct? Right? And then PdV is positive or negative. Minus PdV is positive or negative. It's positive. It's positive, right? That means the internal energy of the gas increases. Correct?
Yes.
Right. So that's the reason we use this kind of definition. Okay? So that's make the job easier. But of course, you can put a positive sign, but then you need to redefine the dV. Okay? But let's stick to this definition and make the job easier. Okay? But not necessary. I mean, just like you, just like everybody, we can choose the easier life. We can choose the, more difficult life, just like me. Doesn't make any change. Doesn't make any difference. Okay? Because in the final destination the same. Okay? But you can go to the easier way. You can go to the difficult way. The same way. So if the piston goes up, then the dV is positive, right? The negative PdV become negative. That means the total internal energy decreases, okay? Because it's doing some work to the external environment, correct? Okay. Any questions? Okay. If you have no questions, let's move on. I'll give another definition, okay? So we know the PV, this is relatively easy and very intuitive, right? And for the delta Q is something different. Okay, so for some system, through the entire thermodynamic process, the system does not absorb any energy or release any energy to the environment. Okay, for example, you have a tank. It's a tank of gas as well. And then we cover the shell of the tank with some thermal isolation materials, okay, foam or even vacuum, whatever. So we prevent any kind of thermal exchange, the heat exchange. So for that process, we know that delta Q will become what? For example, if I isolate the system, thermally isolate the system from the environment, for example, like the cup, for example, like the cup. I have no idea what it is, okay? And do you know that these have two layers, right? So what's in between? What's between the two layers?
Air.
Huh?
Air.
What's that?
Air.
It's air, right? Ideally it should be vacuum. That means nothing, okay? What's the purpose of vacuum? Vacuum just to prevent any kind of thermal exchange. That means the hot water inside will keep hot for a very long time. Ideally for infinite time, but of course not the case. But you can also put the liquid nitrogen in, you can hold the tank. But if anybody wants to play with liquid nitrogen, you can come to any. My lab don't have liquid nitrogen, unfortunately, but you can play with it. Anyway, so for that case, if I thermally isolate an object from the environment, what about delta Q?
It goes to zero.
It goes to zero, right? If I thermally isolate the object from the environment, then the delta Q always equals to zero, okay? And for this kind of delta Q equals to zero process, we give a special name. You know that the physicists always, the process we will learn is kind of physical science. majority of the time, you just memorize different kind of like terminologies. Okay. So what's the name of this process if delta Q equals to 0? Adiabatic. Okay. Adiabatic process. Okay. Adiabatic process means the thermal process does not have any kind of thermal exchange. Okay, that's adiabatic process. Okay. Let me put the equation here. So for the rest of the class, we're going to use this equation quite often. Okay. Okay. So and we can also recognize this equation as a special case to as the first law of thermodynamics applied to the ideal gas, or apply to the gas. Okay. Because for the gas, we can define the delta W in this term. But for other systems, not necessarily, right? So if we have time, we're going to discuss other cases, but if not, we can go to a textbook. At the end of the first chapter, they have different other systems. For magnetic systems, the delta W can be defined as minus H times B. Okay, this one is this is not the entropy. Okay, this is magnetic field. Or you can use something at some other level. Okay, magnetic moment. This is magnetic field. You know what I'm saying? And you can also define different kind of other systems. But anyway, so that's not the object we're going to talk about today. But till we confine ourselves to an ideal gas, it's already or gas. Okay, it's already complicated enough. Anyway, any questions? The question, right? So we talk about the special case. Okay. We know right now that if delta Q equals to 0, this one we call it the adiabatic process. Okay. Adiabatic. And what if a system has a constant volume? What about the system has a constant volume? We know that for a constant volume process, we know that dV equals 0. Correct? That means the du simply equals to that. And for that one, the du equals to minus P. Okay? These two extreme cases. Okay? So for adiabatic process, the change of internal energy only equals to the work. Okay? Only equals to the work. And for the constant volume process, the change of internal energy only equals to the heat exchange. Okay? But there's a problem. There's a problem. You can see in that kind of sense, for that one, I already mentioned, right? I already mentioned this one actually is a TDS. Okay, this one is already TDS. Basically, it means what? Basically means right now we are defining the U as a function of the T and the V. Correct? We are defining the U. We select the independent variables as T and V. Correct? Because you can see the independent variable is V, and of course we know that this depends on T. Although we do not put T. We did not put T here right now. That's the job for the next chapter. But anyway, so right now we know that we select the T and V as the independent variable for U. Correct? Because we only have three, right? We only have three parameters. We only have three independent parameter T, V, and P. Correct? Right now we select T and V. Correct? We do not use P anymore because if the P, T, and the V got determined, the P automatically got determined as well. Correct, everybody? Is that right? Everybody got what I'm saying? But here's the problem. Think about it. We're doing some of the chemical reactions. Do control the volume. For example, you put the acid and the base in the same container and you generate some salt or whatever, or you put the hydrogen and the oxygen together and burn them, and then you generate the liquid, you generate the water. Do we control the volume? Do we seal them in a constant volume without changing? is not always the case, correct? And think about it. The reason why for the material science or even like the Department of the Mechanical Engineering, they very the thermodynamics is a very important class, very important fundamental class for all the departments in the engineering department. But for most of the thermodynamic process we care about, we do not control the volume. Okay, think about it, if you want to generate some alloys from the steel, the carbon, whatever, carbon and steel phase diagram, whatever. I'm really bad at it, okay? So we do not control the volume, right? Instead, we can easily control what? We can easily control the pressure, right? Because all the reactions happen in the atmosphere, so the pressure equals to 1 atmospheric pressure, correct, everybody? So in that case, it's not very easy for you to use this equation anymore, because the volume can change. The volume can change, okay? So think about it. If we have a tank, we put the chemical A, we put the chemical B, mix them together, they have a reaction, and eventually the final product also exposed to the atmosphere. The pressure is constant, but the volume can change. Correct? The volume can change. Right? The volume can change. If the volume change, we need to consider the contribution of this term to the internal energy. Right? And sometimes this change is hard to measure. It's not very convenient for us to measure the changes. Think about it, you do the chemical reaction. We not only need to know how the reaction happens, we also need to measure the volume. Right? It's not very realistic. Correct? So the question is that, is there any way for us to find another parameter, not the internal energy, but another parameter is a function of T and P? Okay. Another is a T and P. And then for the constant pressure process, it only depends on temperature. Is that possible for us to find this kind of process? Okay. This kind of parameter. To understand how can we find the parameter, we have two ways to find the parameter. One thing is only from mathematics. The other one is from the physical argument. When we try to understand the thermodynamic process, always try to understand from these two ways. Understand the same? Understand, derive the mathematical expression first, and then try to understand what it tells us. What's the meaning of it? Okay, if you only do the mathematics, probably wrong, and you will not truly understand the physical process. You know what I'm saying? And on the other hand, if you only focus on the physical process without having very precise mathematical expression, probably your picture is not accurate. You know what I'm saying? So we always, when we learn thermodynamics or any kind of process, involve the mathematics, trying to try our best to understand both ways. Okay. First of all, let's talk about the mathematical point of view. Okay, mostly from mathematical point of view. We know this one is the derivative, right? And this one is also derivative. Okay, so it's simple. So we want to get rid of this term, correct? We want to get rid of the term depends on the change of v, correct? So we can do something like this. Okay. So we just add this term. Okay? And we can just add this term. Right? Okay, this term got disappeared, of course, right? But on this end, it's not a full derivative anymore. It's not a physical, it's not a parameter anymore. It's not the thermodynamic parameter anymore, correct? Because of what? Because this term actually is delta W, okay? This is not thermodynamic parameter, correct? So this term is not thermodynamic parameter anymore. So how can we fix the issue? We add another term. Okay, it's VdP plus PdV plus du, and this one equals to delta Q minus PV plus PdV plus VdP. Okay, and of course these two terms cancel each other, right? And for that one, it's the full derivative of Vp. Okay, that's the vice president. Is that correct? and then it's become d u plus Vp equals to delta Q plus VdP. Correct, everybody? And you can see that V is the thermodynamic parameter, and P as well. And Vp definitely is the thermodynamic parameter, and plus V is also thermodynamic parameter. Correct? And you can see this is the full derivative. Good shape. Okay, and then we define this one as well. We give another name, another terminology shows up. Enthalpy. Okay. I don't know what's the reason for that, but it's really weird name. Anybody knows the origin of it?
No, I was just asking what VP is.
VP is the volume times pressure.
Okay.
Yeah,
But
that's
what
it.
is it? That's it?
That's it. It's not vice president, okay? It's called enthalpy, right? Correct, everybody? Then we have enthalpy equals to what? U times Vp. That's the definition. We define enthalpy as the internal energy plus volume times speed. Okay, of course, this is only for gas, okay? This is only for gas, but it's for magnetic system, it's not Vp, it's something like mu times B, something else, okay? But for the gas, it's V times B, okay? Only for gas, okay? And, of course, the dH equals to delta Q plus VP. Correct? Of course, you can also derive, I just copy this equation, but you can also derive this equation from this definition. Okay? You can also derive it, direct the derivative, right? Then the du equals to delta Q plus minus PdV, and this one is VdP plus PdV, and then cancel each other. You still have the same equation. Okay, this is only from mathematical argument. Okay, this only comes from mathematical argument. Yeah. This is only from mathematical argument. Correct, everybody? So what's the physical meaning? Why such a definition can help us to solve the problem? Why such a definition can help us to solve the problem? You can see that we just add a term of Vp to the internal energy. Correct? Now think about the physical process. Right now, we have still the gas, okay? We have piston here. So we warm it up, we put the heat in, and the gas got expand, right? Gas got expand. Correct, everybody? But the pressure is constant. By adding this term, by expand, it's lose some internal energy, correct, everybody? It's lose some internal energy because dV is positive, and then for the definition, the work is negative, right? It's doing some negative. It's doing some positive, but the internal energy got decreased. By adding this term, we compensate for the decrease, for the loss of the internal energy. Understand what I'm saying? It's compensated for this term. So then, the change of the entropy only corresponding to the delta Q. Okay? Only corresponding to the delta Q. So we have another equation. It's the dH equals to delta Q plus VdP. Okay? That's what's the beauty of it. And then again, for the delta Q equals to 0, this is the adiabatic process. Then the dH equals to VdP. Okay? That means if you want to change the entropy of the system, you change the pressure. You don't need to change the volume, you need to change the pressure. Okay? And then for the constant pressure process, dH equals to delta Q. Okay? So basically, for any kind of chemical reaction, for the forging, changing the metal to different alloys, we generate heat, or the system absorbs heat or generates heat. The change in heat equals to the change of the enthalpy in the constant pressure situation. You know what I'm saying? For example, like this one, we input the heat. Okay. both entropy and the internal energy changes. Okay, but the entropy change equals to delta Q. But for the internal energy change, we also need to remove the work is done to the environment. Okay, basically, for the delta Q, we have two effects. Okay, one thing is got stored in the internal energy, and one part doing the work. Okay, doing the work. Okay, and then if we put them together, this is what? This is entropy. This is entropy. Okay, and the entropy equals to delta Q. That's the physical meaning of the entropy. Did I make myself clear? Just raise your hand if you still got confused. Confused.
Use its beam.
Ah?
Can you re-explain that again?
What's that?
Can you re-explain that again?
Yeah, sure. Let me erase that one. So definition is clear for everybody, right? The mathematical part is already. So let's make these clear, okay? So it's U, Vt versus. All right. Now then, we have a piston. We have another piston, a tank. Okay. And then here's the piston. Here's a cap. Okay. Here's the cap. So let's fix the volume of this system. How can we fix it? How can we fix the volume of this system? We just put a nil here. Okay, nil is down, nil is down. Okay, just nil. We just fix the piston, do not allow it to move. Okay, just like the car sitting down the road can seize to the cylinder. Okay. Anyway, so right now we heat it up. What's the change of the internal energy of the system? Huh? Yeah, I know that. What's quantitatively? What about the du? Equals to what? Everybody agree with me? Make the job simpler, right? We do not consider because we don't need to change consider this term because we know delta V equals 0, right? What about this one? Right now the piston can move freely. We put heat in, we warm it up. Think about it. What will happen to the piston if we warm it up? What will happen to the piston? It's going to go up, right? This is how your car works, okay? If you warm up the piston doesn't go, then your car is broken. This goes up. Correct? This goes up. Then we have the change of volume. Correct? So what about the change of the internal energy here? It's complicated, right? Because you need to add heat and also remove the work done by the piston. Correct? But what about the entropy? The entropy simply equals to delta Q. Right? We do not need to consider the contribution of this term anymore. This makes our job easier. Correct? This makes our job easier. Got what I'm saying? Yeah. So the reason, one of my purpose was to define the parameter named entropy is just we want to make the job easier. Because we can very easily measure the change of the Q, but it's always difficult for us to measure the work done because it's so complicated. And this is very regular shape. But for most of our reactions, probably the shape is really random. So it's not a good idea for us to use internal energy to describe the state. Okay, instead we use entropy to label the state. Is that clear, everybody? We're going to play this trick quite often. Okay, have you ever heard about the free energy? How many free energy we have? What are they? We have one is the the Gibbs free energy, and the other one? Yeah. How to pronounce that one? Helmholtz or Helmholtz? Yeah. One is G, the other is F. Right? Since you already learned something, we can talk about it. Okay? One is F, the other is G. What's the difference between them? Exactly the same thing here. Exactly the same thing here. So what is the Gibbs free energy? What's the definition of Gibbs free energy? What's the definition of Gibbs free energy? Can someone tell me? I forgot. Is U minus yes, huh? Or something else? I think no, it's the F. The whole mass free energy is the U. Okay? Then you know that F is a function of V and T because U is a function of V and T, right? So this is not suitable for the constant pressure process. This only work for this. I mean, not only work is more suitable for the constant volume process. So in order to use the free energy for the constant pressure process, we redefine that one. Exactly the same thing. Exactly the same thing. Okay, we want to compensate for the change of volume. But anyway, so if you don't know what I'm talking about, I'm going to talk about later. Okay. But remember the trick we play with. Okay. Is that clear why we want to select the entropy for the constant pressure process? Everybody understand what I'm saying right now, right? Online students, if you don't understand, raise your hand. Okay, nobody raise their hand. Anyway, just drop a message, okay? If you don't understand what I'm talking, just drop me a message or come to my office during office hour for the online student. I understand quite a lot of people cannot show in person. I mean, that's fine, they have some other jobs to do. But anyway, so I do not want that to become a reason for you to prevent you understand the problems. So if you have any kind of questions, just feel free to drop a message. All right, so let me see. And once again, remember the definition? The entropy is also a thermodynamic parameter. That means it's only defined by the final and initial state. It does not depend on the specific loop. How the entropy change from one state to the other. It does not depend on it. It's a state parameter. It's a thermodynamic parameter. Only decided by the current state of the system. You know what I'm saying? So that means if you have a system at the beginning, in the A state, you have entropy A and TA and PA. And you have a final state is HB, TB, and PB. If I ask you to calculate the change in the entropy, you can create any kind of loop. Okay? You can create this kind of reaction loop. A to C to B, or A to D to F to C to G to whatever B. All of them should give you the same result. Okay? You can select any kind of reaction loop, link the A and B point for you to calculate the entropy. Understand what I'm saying? Let me give an example. Okay, this example actually already shown on the textbook. This example already shown on the textbook, but I can repeat that again in the class. Okay. There's an example. Okay. So consider reaction. Consider reaction. Right? We have the two ions and react with three half of oxygen molecules. So the final product is Fg2O3. Okay? So actually, we do not have this reaction naturally happen. We don't have this reaction. It reacts, but it doesn't happen. We cannot create this reaction very easily in the lab. You know what I'm saying? Typically, the ion does not react with oxygen directly generate this kind of final product. You know what I'm saying? But I want to ask how much heat got generated from the process. I want to ask you to calculate the heat generated by the reaction. Remember, all the process happened under the atmospheric pressure, so it doesn't change, right? So the pressure doesn't change, correct? So the heat generated by this process is just a change of the enthalpy, correct, everybody? So the enthalpy change equals to the heat generation, right? Because this is a constant pressure process, correct, everybody? I want to ask you to calculate this. So how do we calculate? Or how to determine it? Huh?
Disassemble the oxygen into oxygen atoms.
I'm talking about the measure it. Of course, we can calculate, I mean mathematically, but how to measure it? We cannot make this kind of reaction in the lab, but we can make this reaction, okay? We can make this reaction. Okay, how does the reaction happen? We just put the ion and the pure oxygen and burn them. Okay, have you ever done this experiment in the chemical class? Have you seen that before? You just have the piece of the iron and warm it up and put in oxygen, it's good, yeah. Just like firework. Okay? We know this reaction, we can measure the change of entropy or the change of the heat generation from this reaction. Okay? The other reaction is like this. I'm not a chemical guy, okay? So please, pardon me, just copy what's in my document. This reaction also happens, okay? So we know that this one. All right? So this is our final destination, okay? This is the final destination. This is our the starting point, okay? Then what? We can link the starting point to the final destination. We can separate into two steps of reactions, correct? The first reaction is we have 2/3 of the reaction, right? And then for this reaction, we have what? We have 1/3 of this reaction. Okay? If you sum them together, you generate this first reaction equation. Is that correct, everybody? If we have 2/3 of this reaction plus 1/3 of the reaction, we replicate this one. You just replace the number. Okay? Think about it. So you have 2 ions, and then 2/3, then you have what? 2 ions, right? And for that one, we have 2 ions, and then they have totally what? 6 ions, and 32 ions. Okay? Numbers are right. So in that case, the totally heat generation generated by the process simply equals to okay? So this is how you link this reaction loop. You can, of course, you can find other reaction path, but all of them should give you the same result. Okay? What's the reason for that? The conservation of the energy, of course. All right. Any questions? Hey guys, we only talk about 2 very fundamental parameters in thermodynamics. Okay, we have more and more coming up. We have entropy, we have free energy, 2 types of free energy. Okay, and we have the partition functions. We're going to make your life very miserable. I will try my best to explain the purpose of each parameter and the relationship between them. Okay, but first of all, I'll try to understand why. I think I already making myself understood why we define entropy. But if not, I can try again. Okay. We talk about internal energy. First one. This is a variation of the first law of thermodynamics in the condition of constant pressure. Okay. These 2 fundamental equations. And then so far we are done with the first chapter already, but we want to apply the knowledge we learned to the very specific systems. So in order to make your life really hard, we introduce another concept. Just to make just showcase my value to stand here to give class. We just leave here. Okay, we introduce another concept. We call it, what name of it? Oh, heat capacity. So what is heat capacity? That means the temperature change. If I warm up some, if I give the heat to a system, I want to see how the temperature changes. Okay, how the temperature changes. Okay, this is defined as, we define the heat capacitor in that way. Okay, that's the definition. If I input the heat into system, the temperature is going to change. We assume in a very small range they have a linear relationship, and then the linear factor is the heat capacitor capacity. Okay, capacity. Or in other words, okay, is that clear? It's just a definition. Definition, okay? No argument, okay? This is the definition. Huh?
What is the difference between the delta and
We want to label. The delta means this is not a derivative. If we put the d, that means this is a derivative of the thermodynamic parameter. But since Q is not a thermodynamic parameter, then we use the delta Q to label the change of it.
So
Okay.
that's a D on the bottom.
Yeah. And the other thing is, for the dt, you can draw it on the figure. Okay, you can draw in the xy, the reference frame. And xy is not reference frame. The xy, a coordinate frame. Okay, but for delta q, typically you cannot. Okay, we know that you have change, but we don't know the loop. Okay, that means it's loop dependent. This one is not loop dependent. Okay. Okay. Anyway, so this is definition. Okay, no argument. No negotiable, okay, this is just definition. Okay, then here comes the interesting thing. See that one? For constant volume process, we have what? du equals to delta q, correct? And equals to what? C dt, correct? And this one we label it as a constant volume heat capacity. Okay? And of course, we can also, for the constant P process, that means the constant pressure process, we have the dH equals to delta Q. We can put it here something like this, okay? So this one, delta Q, we just put it. We put a bracket and what's the name of it? A small
Subscript.
What was it?
Subscript.
What about on that corner?
Superscript or exponent.
Whatever. It's different or something. So this one is the Cp dt. Okay, Cp dt. So this is the constant pressure heat capacity. This is constant volume heat capacity. Okay? What's the relationship between them? What's the relationship between them? They are not the same, right? They are not the same. Why they are not the same? Think about it. For the constant pressure process, we absorb the heat. We also do some work. But for this one, we do not do any work, right? So all the energy used to raise the temperature. But for the constant pressure process, partially a part of the heat got warming up, but the other part doing the work, right? So that which one should be larger? The CV larger, CP is larger. CP is larger, right? Think about it. I give the same amount of the heat to a system. For the constant volume process, all the heat transfer become internal energy and warm the system up, right? And then that means the delta T is for the constant. If I have the same amount, if the Q, delta Q is a constant, okay, is a constant. If that delta Q doesn't change, I give the same amount of delta Q. Then for the constant V process, the dt is larger, right? For the constant P process, the dt is smaller, correct? Because part of the energy become work, correct? Is that true, everybody? So in other words, Cp should be higher than Cv, correct? Because what? Because Cv equals to delta Q dt for the constant volume, and Cp equals to delta Q and dt constant P. Okay? We have the same amount of Q. The temperature for the constant volume process goes up higher, and then Cv is smaller. And this one, the dt becomes smaller and Cp larger. Correct? So right now we know, the general case, the Cp should be larger than Cv. Cp should be larger than Cv. Right? Constant pressure heat capacity should be larger than the constant volume heat capacity. But what is the specific?
Could you explain that again?
Huh?
Could you explain that again?
Okay. Why this one is larger than that one?
Yeah.
Okay. We have a tank. Okay, we still have, let's talk about we have two tanks, okay? One is the piston is fixed. We pin the piston here. We pin the piston here. It doesn't move, but this piston can move freely. We give a certain amount of Q. We also give a certain amount of Q to the system. We warm it up. But if the piston doesn't move, all this heat will be transformed into the internal energy, correct? And used to heat up the system, correct? That means all this one become delta T, correct? For the constant volume, okay? Now for this case, if I warm it up, the piston going up, right? The piston go up. Correct? It's also output some work, mechanical work, do some work to the external environment. Correct? Then we have two parts. Part of the delta Q become the delta W, and the other part used to warm up the system. Correct? It's also warm up. So which one is larger? This one is larger or this one is larger?
The second one.
Huh?
The second one.
What do you think the second one is larger? Think about it.
Are you asking if delta Q is, which delta Q is larger?
No, I'm asking which delta T is larger. Delta TV is larger or delta
Oh yeah,
TV?
delta, okay,
TV is larger,
yeah.
right? And remember the Q is the same amount, okay? So this one Q is the same amount. Delta T, dt in this case is larger, correct? This one is larger, this one is larger. And this one smaller, this one smaller. But Q the same amount. If this is small, if this one large, then the capacity is small. Right? This one is not small, this capacity is larger. Right? So that's the reason we have this relationship. Correct, everybody? Then specific to the ideal gas. Specific to the ideal gas. Let me see. I don't want to make any kind of stupid mistake. Okay. Remember, the dH equals to du what? Plus PV. Oh. No. H equals to what? U plus PV for gas, okay? Correct, everybody? And what's PV for ideal gas? Energy. Correct, everybody? Is that correct? And then the dH equals to du plus nRT. Is that right? And remember that, where's my definition here? Anyway, may I read this part? I think we have enough time to record it already. Then what we have is dH. What we have is partial H, partial T, partial U, partial T. Correct? From that equation we get this one. Right? Is that correct, everybody? And then we have, this one is what? This one is P. This one is what? This one is CV. Equals to RT. And for one more of atoms, for one more gas molecules, n equals to 1, right? And the Cp equals to 7. Okay? I mean, M means molar, okay? For molar, I mean molar specific heat energy. Okay, you can see that, yes, indeed. The constant pressure thermal energy, heat capacity is larger than the constant volume heat spent by a factor of ideal gas constant, okay? For 1 mole of gas. Any problems? Any questions? Actually, there's one thing. It's not very strict here. There's one thing that's not very strict here. I have no idea whether you identify or not. We define the Cp as the partial T in the constant pressure. But for here, I did not emphasize that one. I did not emphasize the constant pressure. And for the CV, actually is the partial U, partial T as a constant volume. But I did not highlight that either. I direct jump to this step.
Is that because when we're dealing with enthalpy, then it's like a constant pressure, and when we're dealing with internal energy, it's constant volume?
Partially because of that. And the more accurate statement is because U is what? Is the thermodynamic parameter, and it's not only it not depends on the path. Actually, for the ideal case, we will find that U actually is only a function of temperature. And of course, H is only temperature, function of temperature for ideal gas. Okay, that's the reason we do not need to, emphasize that one. And eventually, you will have U simply equals to CV dt, and H equals to Cp dt. Okay? Just remember that first. I'm going to spend about 10 minutes to prove it. Okay? Why is like this? For ideal gas, okay? For ideal gas. Why it looks like this? Why we do not need to emphasize the P and the V in this equation, okay? But this is only for ideal gas, okay? For other systems, not the case, okay? But right now, you know that we have two capacitors, okay? One is constant volume, one is constant pressure. order to make the online student have the clear. So we define the CV as partial Q dt at constant V, okay? And we define CP as the delta Q dt at constant pressure, okay? This is what we have, okay? And for constant V process, we also have the du equals to delta Q. Then we have CV. Okay? And again, for this kind of the constant P process, we will have similarly, we have something like this. And then we will find the CV actually equals to what? Partial U, partial T, V. This is the accurate expression, okay? This is the accurate expression, okay? And in other words, if we want to calculate the change of the internal energy, we will have CV and dt under this one, delta H. Again, this only happened on, right now this only happened to this only apply to the constant volume scenario, and this one only apply to the constant pressure scenario. Okay? Any questions? I just repeat what I just summarized. Okay? What I'm doing. Okay, so let me see how can I make the job easier. We need to calculate the term. Okay, think about it. So for this one, I mean, we need to calculate one term. We want to know. We know that U is as a definition, we know that U is a function of V and T. We know that if we change the T, the definitely internal energy changes. Correct, everybody? Then the question is, what about this term? What about this term? What about this term? Right? Think about it. So for this one, what we'll have is the du equals to partial U, partial V, T plus partial V, partial T, V. Correct, everybody? Oh, sorry. No, not correct. This is correct. Right? So you can see that for that one, we know this is CV. Correct? Yeah, we know it's CV. What about this term? What about this term? Any ideas? Actually, from experiment done by this guy, he said this term equals 0. He said this term equals 0. But what's the reason for that? We cannot prove it. We cannot prove it, okay? We cannot prove it mathematically. But this conclusion first come from experiment. He did one experiment. It's like we put the gas, we first of all seal the gas in half of the tank. In half of the tank. This part vacuum, okay? And then we remove this one away and make the gas freely expand to occupy the entire container. You know what I'm saying? Then what? The volume change, right? And he find that the temperature doesn't change. Still have the same temperature. You know what I'm saying? That means this term, yes, that means this term, that means this one, duplicate this condition. That temperature doesn't change, constant temperature, and the volume change. You know what I'm saying? But this doesn't do any kind of work to the outside. And do not absorb any energy from outside because temperature doesn't change. right? Then the total internal energy doesn't change. Then this term equals 0. You know what I'm saying? Because there's no work done by the system because it's a tank. We just remove the separation in between. It's freely expand. Do not do any work. Right? Then the delta W equals 0. And the temperature doesn't change. Then there's no thermal exchange.
So when you remove the partition, the particles move, but
Yeah.
you said the volume does not change?
The volume change, but it doesn't do any work.
So no pressure change?
No pressure. I mean, pressure also change.
So then how is there no work?
But, I mean, it's free expand. It doesn't, I mean, just like, for example,
Oh,
I'm flying from this end to that end, but I'm not pushing anything. I don't do any work. This is a really weird argument.
yeah.
But anyway, so his argument, okay, you do not blame me, okay, it's not I blame him. Okay? The work equals 0, right? Because you do not have any kind of the mechanical interaction from the gas to the external environment. And he found the temperature doesn't change. If the temperature doesn't change, that means the delta Q, then the temperature doesn't change, it doesn't have any kind of thermal exchange with the external either, right? Then the delta Q is sort of 0, right? Then the delta U also equals 0, and then this term becomes 0. That was his argument. But actually, this is not the case. This is not always right. But what's the reason for that? What's the reason for that? What is the reason for that? The reason is we are dealing with ideal gas. So what is ideal gas? What is ideal gas? Ideal gas is kind of a tank of gas, and every molecule is only a rigid particle, dimensionless particle, right? It's a dimensionless particle. The only interaction between them is just collision. When they have the head-to-head collision, they just scatter to each other. Okay, there's no other terms of energy. The only internal energy got stored by the particle is what? Is the kinetic energy. Okay, all the internal energy, just the sum of the kinetic energy of each of the particle. Correct, everybody? So that means no matter how large the room is, the kinetic energy doesn't change. Right? You know what I'm saying? So you can say that if I'm jogging, if you want to lose some weight, you can jog on the treadmill. You can also jog in the playground. You use the same amount of energy, no matter how large the field is. Correct, everybody? So this is the consequence. This is the result of the ideal gas approximation. Okay? But why I'm saying that this is not always the case? The reason is, for the actual gas, they have molecular structures. Correct? They have the molecular structures. That's the reason when you cool it down, it becomes liquid. If there is no interaction, you cannot liquefy it. Right? Correct, everybody? You have the structure, for example, like water, it just looks like this. Right? And for the carbon dioxide, it looks like this. Correct? You have the structure. They have the interaction. Then this term doesn't work. Okay? Then you have this kind of free expansion process. The temperature of the gas can increase, can decrease. The internal energy will going to change. The reason is that the system will not only have the kinetic energy, it also have the interaction between each other. So this becomes stored as a potential energy between each other. You know what I'm saying? They can be attractive, they can be repulsive. Okay? Some gases are repulsive, indeed. Actually, this is for that one, this, for example, is still the same thing. So we have some gas trapped on half of this cylinder, and in between, we put some membrane, very tiny holes, and then the molecule can escape from the hole and got released to this kind of empty space. You still do not do any work, but you will find temperature change. Okay, the temperature is going to change. This is the principle of the refrigerator. You compress the freon and got this kind of free expansion process is done cooling down, right? Because you have the interaction between molecules. Okay, and some molecules, if you expand it, it's going to warm up. It's very anti-intuitive, right? You know that expansion always cool down, but not always the case. Okay, one example is helium. Okay, if you pass through the helium to a very narrow channel, it's warm up. Okay. Yeah, you can try. You can come to my lab to try. But this is for the real gas. But for ideal gas, this term becomes 0. But for real gas, it can change. It's not always 0. Okay. And this kind of effect we call it. We name it the Joule. How to say that? Joule. Yeah, Thomson effect. Thomson effect. Thomson effect. Will expand the temperature change. Okay. But forget about it. For the ideal gas, this term always equals to 0.
But Professor, you mentioned something that we cannot prove it mathematically.
We cannot prove it mathematically.
Why?
Because this one, of course, if we have ideal gas model, we can prove it mathematically from ideal gas, right? Because this term is what? This term is just potential energy. We know there's no potential energy. This term becomes 0. But the first, the Joule, he makes the claim from experiment, okay? And that means, you cannot, what I mean is that you cannot get this conclusion only from thermodynamics. We need to have more knowledge about the specific structure of the gas we are dealing with. Okay, but if we know that this is an ideal gas, we can prove it is equal to 0. Okay? Okay, this is very important. It's only work for ideal gas. And then we know this term equals 0, then what do we have? Then du is simply, you can see that. We know that u right now is a function of t and v. Right now we know that it's independent of v. Correct? Do you think it's dependent on p anymore? It's not dependent on p anymore. What's the reason for that? Think about it. We have v, p, t. We have 3 parameters, and only 2 of them are independent. Right? Right now, the u depends on t, and it's independent on v. It must be independent on p. Otherwise, all 3 parameters become independent, right? So then, it's not a parameter of p either. Then the u is only a function of t. It's only a function of t. Correct? Right now, so because of that, we do not need to emphasize this one anymore. Okay? The same argument here, only for ideal gas. What's the reason for that? U, we know that it's only a function of p. For ideal gas, and plus PV. And for ideal gas, the PV equals to what? The PV equals to nRT. It's only a function of t. In that case, because of that, alpha p is only a function of t. Okay? Then we do not need to emphasize it's a constant pressure process anymore. Is that clear, everybody? And then go back. This relationship is a precise relationship. Okay? We do not need to emphasize the process. We know that this one is always true for ideal gas. This one is always true for ideal gas. Okay, I think that's pretty much what we're going to talk about today, and we have not finished yet, but we're going to talk about next time. Okay, at the beginning of next time, we're still going to deal with the first law of thermodynamics, but I will give you some practice. Okay, do some practice next time. So you're going to do some calculation on your own. Okay, to see whether you understand or not. Okay, but anyway, so spend some time to read the textbook if you have. Okay, but if you do not have a textbook, just borrow some. Anyway.
Enthalpy is Greek. It just means to heat up enthalpy.
Enthalpy, yeah. Just about the heat. Yeah. Question?
I have just one analogy. I have one analogy
Yeah.
with the heat capacity.
Yeah.
May I share it?
Yeah, sure.
Suppose heat capacity, equilibrium, in my understanding, capacity means the resistance to change.
The what?
Resistance to change.
Uh-huh.
Suppose I am putting force, if it can resist its capacity is more. And for capacity, resistance to change. So if this is one water container, this is another one container.
Yeah.
Which plate has the container has the more capacity?
Yeah, yeah.
We consider the one which is wider.
Yes.
So to increase the height, I need to give this much of water. To increase the height, I need to give more water
Yeah.
for this.
Mhm.
So to change the height, it resists more. We need more water
Yeah, yeah.
to change. So in case of heat capacity, suppose water, if I want to increase the temperature by 1 degree,
Yeah.
it can absorb more heat.
Yeah, that's right.
That's why we say like the heat capacity of water is more. To increase the temperature by 1 degree, it can absorb.
You can do this kind of analog. I mean, it's fine. Yeah, it's fine.